GD302, and again, we're just going to observe address space layout randomization. So we launch a developer command prompt using Visual Studio, any version, and then make this program called esp.cpp. So I've got that here. I can type esp.cpp. All right, what this is going to do, it actually includes inline assembly code in C, which you can do. So I define a data variable, then I move the ESP into there, and then I just print it out. So you can see the stack pointer inside here just to see address space layout randomization running. And I've compiled it as usual. And so if I run that, I don't need / in Windows. All right, esp.exe. Okay, it prints out this value D3FECC, and if I run it again, it has a different value. It has a different value every time I run it. That's address space layout randomization. Each time you launch the program, it randomly relocates in memory. Now you can turn that off. And you can do that by compiling it differently. Yeah, I called it ESP2 with the same source code. You use /C to only do part of the compiling it down to object code without linking. And then in the linker, you add this flag dynamic base : no. And that will not give it the relocation section it needs to relocate in memory. So esp2.exe created with that compiling process is not randomizing. So esp2.exe, if you run that and then run it again, it always has the same location of the stack. Every time you run it, it's not randomizing in memory. All right. And that's why really old code, like we saw, Vuln server has code that does not relocate in memory. All right. So here I'm making another program called PWD3, compile it without. All right, and ask for a password. Okay, now we run it, it's going to tell you to fail. Okay, so if I run, this is going to be PWD, the same old thing we've seen before, PWD3.exe. Okay, you ask it for a password. If you get the wrong password, you get fail. If you run it again, it also failed. Notice it's not moving. The ESP is always at the same location. So this was compiled without ASLR, so we can perform a buffer overflow inside the debugger, which might be another way to see it to understand how it works. So you install it, run it in Immunity, PWD3. We've already got Immunity on here. Okay. And we load PWD3. All right. All right. And let me go back to here. All right, so I run it, fix the font so you can see it, and now I'm going to enter a password of 32 letters. So I run it here, and that's going to hit a breakpoint. Now I'm going to clear these breakpoints. Let's do view. We'll put them back in, but they're in from my test earlier. There's my breakpoints, and let me change it, the font, so this is visible. Font, OEM. All right, and now I can delete it. I think just delete will do. No. Right-click. Nope, just appearance. Well, I'm having trouble deleting the breakpoints. There is some way to delete breakpoints. I know how to do it back from the other window. If I go back to CPU, I can delete them here with function F2. Okay, I'll do it that way. I thought there was somebody to delete them in that other window too, but I can't figure out how to do it. All right, so now I've deleted breakpoints. I'm going to do debug restart. Yes. And then run. And now it should be running in one of these windows, and there it is, asking me to enter the password. So now I give it the password in the clipboard, which is A's, B's, C, D's, a bunch of non-repeating letters, you know. And now it crashes. It doesn't finish. If you look at the bottom, it's got an access violation when executing 48, 48, 48, 48. So it did hit some of those letters, ended up in the instruction pointer. And you can see them here. The EIP is 48, 48, 48, 48. So I've got the simple buffer overflow that gives me control of the instruction pointer. And now I can do the same kind of exploit that we did in the early days on Linux, like in ED202. I can look at the stack at the point of the crash and see, here's where it's going to return to. This is the code that led to the crash. This is how it would return back to it. So you can click that, and you can right-click Follow in Disassembler to see the code that ran before this. And up here it is. And, all right. And so now, this is the code that led to the crash. So I'm going to go back here and figure out how the crash happened. So I scroll back to the start at 40100. 401,000 is where you always see the text section start in Windows. And now I can just go through this, and if I go down screen by screen, I get these points. Here it is sending sort of unreadable junk. If I keep going down here, I'll eventually see readable text. There it is, enter password. So here's where it took the password from the user, and I know that's what caused the buffer overflow, because when I put in a long password, some of the data from that ended up in the instruction pointer. So I want to go to the second call function after enter password and put a breakpoint there. So I'm going to scroll down a little more. Okay, so here's where it prints, this prints the message, enter password. This is what reads from the user. So I want to put a breakpoint there on that call function with F2, function F2 on a Mac, and another breakpoint after it completes reading it in. There. So now this is just what we did in Linux. You put a breakpoint before the buffer overflow, after the buffer overflow to see what's going on. So we should be able to restart it and feed in the data again. Debug, restart. Yes. Then run. Then it hits the breakpoint. Okay. Find ESP and EBP. So you can see the stack frame. We can find the return pointer. So ESP is here, FF04, and EBP is FF24. Okay. In the lower right pane, highlight the stack frame. This is from, okay, ESP, FF04 to 24. This is FF04, and 24 is off the bottom. So I'll make this a little taller. There we go. So this is the stack frame. I've been trying to highlight it with questionable. There we are. That's the stack frame. This is exactly the same process we did before. That's the stack frame, and this is the return pointer. All right. And it is 19FF2C. All right. And that was 400 something here, so let me see. I think I might have something wrong. It must be this thing down here. Oh, yeah, 24 is included. My highlighting was wrong. 24 is included in the stack frame. Whoa, whoa. So this, anyway, the bottom of the stack frame is down there. If I can get this thing to roll down. Okay, there we are. There's the return pointer, 401-248. And you can see that here, 401, it's somewhere in the code section anyway. So that's the return pointer when it returns from this function. And that's what I want to override. So I can do debug run, and I can put in that bad value again. Right? So we run, put in the data, okay. So I run here. Now it's asking for the password. So I put in that password in the clipboard, A through H, and then enter. And now it is the second breakpoint. And now if I look in the stack down here, I see the overflows, A, B, C, D, E, F, G, H. And here's the location after 24 where the return pointer is. There it is, it's the H's. Now what we did before was go write a Python exploit that would put in non-printable characters in the H's, but since we're in the debugger, we can manually change that address. So we can right-click that line containing 48, 48, 48 and edit it, and we can fill in the address of the uwin instruction. So we're going to find the address. Now we should have determined the uwin instruction earlier, which I skipped over. Let me see if I can do it now. There it is. It's going to be down a few pages from the one we looked at before, so I can probably still do it. So I know where I want to put it right there. I just need to find the UN. Now here we are. If I scroll up, this is the enter password. So if I just go down a bit, I'll find the UN. There's the UN. Okay. So that is right here, 401,260. So I want to carefully insert the target address into there, again, making it backwards. So there. When I did it before, it was 401270, but now it's 401260, probably because I'm using Windows 11 instead of Windows 10. Things are a little bit different. So that's what I want to put in here. So right-click, edit, or modify. I think we'll do the same thing. All right, and now I can put it in hexadecimal, which is going to be, let me try the edit instead of modify just to make sure things are right. Okay, edit, there. And now down here I can put those 4 bytes in reverse order, so it's 60, 12, 40, 00. That should do it. Then I say, okay, now that has changed to a proper address. And now I should just be able to run. And now I should get the UN message. And I do. I get the UN message. So that's what I wanted to show you. Unfortunately, this thing has shrunk my font to an insane amount. Control plus. There. Control plus brings it back. Good. There. So there's UN. All right. So that's what I wanted to show you. That's the buffer overflow. And you can also write it in Python, of course, as we did before. But the point is, this is the exact steps in the Windows debugger, so it might make it more clear. That's the idea. Anyway, that's all I wanted to show you for that one.